Hello, team. I'm going to show you how to calculate principal components using a training and test set. Last night we talked about it a little bit, but I didn't really demonstrate the actual nuts and bolts of it. So this is the bank loan test with all the relevant quantitative variables. And what we're going to do is we're going to predict age using these quantitative variables. Anything else in the file is just erroneous. You've got weights and some other things that we're not using. So what we're going to do is we're going to start from the basics. As usual, we're going to go data, select cases, and we're going to split. We'll take a random sample of 80% of the cases, okay? Easy game. So now we have 80% selected. The next thing we're going to do is we're going to do analyze. We're going to look for factor levels, which is dimension reduction, okay? Because that's what we're trying to do with principal components is reduce dimension. Okay? And I'm going to reset this. I'm going to use everything but age and the filter variable. In my descriptives, I love descriptives. I'm going to get a coefficient matrix just for giggles. Extraction, I'm going to extract the principal components. And I'm going to use 3 factors because I know from experimenting that 3 gathers 86% of the variability, just like I showed you last night. You can also get a scree plot, which demonstrates this to know how many factors. But I'm going to pull out 3 factors. I'm not going to do any rotation. Rotation is a mechanism where we can actually not do orthogonal components, meaning independent. I want them independent because I'm going to use them in regression. The scores, I want to save as variables, regression scores. You could save Bartlett or Anderson-Rubin. These are all available, but regression is the typical score for a regression model. So I'll display the factor score and the coefficient matrix, and I'll click OK. Now from this is the correlation matrix, the ones on the diagonal. You can see their years at current address is highly correlated with years with current employer, and household income is the same thing. Some correlation there, not highly, but moderate correlation. And you can see that the extraction of the percent variability is down here on the total variance explained. 3 factors gives me 86.401% of the variance, 75% with 2, and only 53% with 1. We're taking 3 because we wanted at least 80%. And here's the component matrix and how they weigh out if we're to build those, which we're going to. The easiest way to build them, though, is to use this coefficient component score coefficient matrix. This matrix right here is multiplied by the original variables to generate the 3 components. So this is going to be 0.252 by the Z transformed year of current employer, 0.210 by the Z transformed year at current address, 0.255 by the Z transformed household income. So the first thing we need to do is we actually need to Z transform these variables, and then we'll build our 3 components. It's really easy to do. You can see here, we've already saved these 3 factor scores, but since we filtered, we don't have an idea what should be up here, right? We have these empty spots, and these empty spots we need to fill in order to be able to run regression. So how do we do that? Well, first of all, let's just analyze descriptive statistics. Let's get the descriptives for all the independent variables, rather not the dependent. Put them over here. I'm going to save standardized values as residuals. And I'm doing this with a training set selected. Okay. So I didn't do any leakage. Now I have this matrix here. And what I can do is I can grab this whole matrix. I'm going to pull it over to Excel, make my math easy. We'll lighten that up so you can see it. And now you've got the minimum, max, and of course the mean. I didn't grab the standard deviation. I needed the standard deviation. Thought I grabbed it, but evidently I didn't. Oops, it's not showing it here. So let's see if I can't get it to show it here. Okay. Maybe now we got it. I made it larger, and now we have it. We'll try this one more time. Paste it here. There we go. And we'll make this yellow so you can see it. So now we have the means and standard deviations, and that's really what we need. And this is on the training set. And we'll shift cells left. So look at the means and standard deviations. So all I have to do is use these means and standard deviation to calculate the z values for the test set, right? And to do that, since I've already calculated some of them right here, I could fill in those values. Well, the way I'm going to do it is I'm going to delete these. I'm going to calculate them from scratch on the whole data set. Select cases, select all cases. And what I'll do, close this so it's no longer messing it up. I will go here and I'm going to make this a z value. Now remember, z's are nothing more than each observation minus the mean divided by the standard deviation. So I'm going to do that for every variable. In this particular case, transform, compute a variable. Okay, we slide that up, reset. This is going to be z employ, and it's going to be equal to years with current employer minus the mean, which we happen to know is 6.85, divided by the standard deviation, which is 8.18. Okay, all of a sudden, I've calculated z employ. Now, the next thing I'm going to do is I'm going to calculate z current address, transform compute. It gets to be old. You have to do this a few times. Z address equals address minus 6.27 is the mean, divided by 6.02. Okay, so z address, boom. The next one, transform compute. This is why it's easier in syntax sometimes, because you can do these quickly. Z income, and this is going to be income minus 58.0872 divided by the standard deviation. Okay, cool. And then we just got two more to do, so we'll do those. Compute variable, this will be z debt equals debt to income, debt, we'll call this debt income, minus 9.876. So you can, the cool thing is you can really copy from, why isn't it showing up? There it is. You can copy from Excel right into here, so you don't mess up. Now we have two more. Transform compute variable. Excuse me, please. And we'll call this one's going to be credit card debt. And we'll do it this way. Oops, wrong one. So it is a little tedious, there's no doubt. And we'll call this, we'll just make sure this is constant cred debt minus. Notice that we calculated the means and standard deviations on the training set. We did that on purpose because we didn't want to leak information from the test set at all. If you use all the data, you're leaking information, and that's what we call cheating. No, not really. It's not cheating, but it is wrong. You don't want to leak any data. So we got credit card debt, which is perfect. Okay. And then the last one, it's too simple. Transform, compute variable. This one is other debt. The other debt equals other debt minus 3.71. So what this is going to do is it's going to give us variables that are roughly centered at 0, because we're subtracting the mean, and have a standard deviation of 1. Now, we calculated the means and standard deviations on the training set only, so it's going to be slightly different than 0 and 1, but it's going to be close. Z other debt, oops, divided by, oh yeah, what do I have in here? Other debt minus 3.0 divided by 5.05. I think that looks right. Let's do it again. Obvious. Oh, I have two things. Other debt minus, it was hiding that other one, right? And then we'll go up here, divided by, and there we go. So that's there. So if I were to run descriptives on these Z values, I will run quick descriptives, you can see that they're roughly centered. The means are close to 0. They're not going to be exact because we split the training and test set. And we only ran the statistics on the training set. And the standard deviations are close to 1. Again, they're not going to be exact. You're going to have some deviations there. Okay, so we've got those now. So we had already calculated these factor level variables, but we could calculate the factors for all of them just using the training set data by going back up to this component score coefficient matrix. This tells me 0.252 times the Z value of this plus 0.210 times the Z value of this. It makes a linear combination. That's what I tried to explain last night. I'm not sure that that was clear. So what we're going to do is we're going to show you how PCA is really just a linear combination of the variables. Now I'm going to spread this out a little bit, and I'll make this so you can see it. So what this is this is going to be our new variable. This is going to be factor 1. We're going to calculate factor 1 for all of the variables now, transform compute variable, and we're going to call this factor 1. Now we have, I'm going to take out this other debt, 0.25 times Z employee plus 0.210 times Z address plus 0.255 times Z income plus 0.101 times Z debt income plus 0.253 times credit card debt plus 0.261 times other debt. Now this will create factor 1 for us. And you can see that factor 1 is roughly the same within rounding of this factor 1, 1. 0.07 is my filled in value. 2.2 versus 2.14, not a material difference. 0.37, 0.34, 0.45, 0.44. And that's because we have calculated these factors based upon the linear combination generated. And now we filled in the whole data set. Okay, so we've got factor 1. We can do that with factor 2 as well. I'm going to cut this one. Now we'll transform compute variable. This is going to be factor 2. All we have to do is substitute. Where's the components? Oh, I already have them over here. These components in minus 0.288 minus 0.288 minus 0.341 minus 0.341 minus 0.178. See, if we had used all the significants that are on here, we would have had an even closer result. But I'm just giving an approximation, which is perfectly fine. Minus 0.178, 0.626, 0.228, and then finally 0.263. Now, if I were to go through, and I'll show you, so you can see each one of these, when you copy them, they actually have a lot more significant digits. So if I put these in here, I will be almost exactly what that other factor is, okay? I don't want you to think that we're doing anything different. We're just rounding off the significant digits. And I'll do that here for you, just so you can see a little bit better that when you use the significant digits, it's the same thing as what the factor score that was generated. It's just we didn't use the same number of digits. And so you can see that we're just making a linear combination of the z variables for each one of the variables, and we're doing it for the first three. Then I'll put this last one in just so you can see it. You should see it once, and we'll put this in here like this. And so factor 2, click OK. Now factor 2 is created, and factor 2, oops, I have a typo. I obviously have a typo somewhere because it's off. Oh no, is it? No. It's still off a little. 0.6 minus 1.39 minus 1.43, 2.63, 2.62, 1.689. So you can see it's closer. They're using a specific number of significant digits here. I use them all in this particular case, and there'll be slight differences, but there'll be nothing major. So we have factor 2 built. The last thing we'll have is factor 3. Factor 3 is the same way. We just go right here to our values, and I can spread this out, and I can do this. So I can copy this, transform compute variable, factor 3, and we'll just do this right here. Boom. Oops, Control Z. I forgot to go to the top. That's okay. I'll copy them over here. This. Okay. Times Z employ. This. Times the address. This times my Z value for income. This times my Z value for debt income. This times my Z value for credit debt. And then finally, this times my Z value for other debt. Okay, and there we go. And so we click factor 3, okay. And once again, we now have everything filled in, and we have a close approximation. Well, no, it's actually the values that they should be, given we probably used more significant digits than that were used elsewhere. So we get our factors. Now we have all three factors. I'm going to cut. Now it's easy. All I have to do is build a regression on the training set if my filter variable equals 1. So if I look, I've got my Z value, I've got my training set selected, and I've got my factors. I just have to do this, analyze, regression, and we'll go to linear. We'll go age as a function of factor 1, 2, and 3. Okay. Now, on the training set, we can see that I've built this model, and I've got these constants. Oh, the model's significant. We're capturing 83% of the R squared. Okay, I grab the coefficients here just because I can, right? That's what I really need. They're all significant, so what I'm going to do is I'm going to paste them over here again, and once again make this, and there you go. And what I'll do is I'll build my estimates. Now I'm going to build my estimates on the entire data set, data, select cases, all, transform, compute variable, forecast. Okay, and I'm going to delete all these. I'm going to copy this over. And I just paste it in. 34 plus 8.69 times factor 1 plus, it's the old regression technique, times factor 2 plus 5.64 times factor 3. And I click OK. There's my forecast. And I forecast the entire data set. Now, I can go ahead and do my mean squared error as well. I just transform compute a variable. I'll filter for the test set afterwards. I'm going to call this the sum of the squares error. And it's going to be my observed minus my expected, which is age minus my forecast age squared. Okay? do that again. Oh, I forgot to delete the when you copy and paste, you have to be sure you delete age minus forecast age squared. Okay, good. Okay, now to evaluate how I did, I'm going to one more time select cases, but this time I'm going to filter. Now you've got my training set. I'm going to filter my test set. The way to do that is just to toggle twice data of transport select cases. Toggle this to 0. Okay. And now when I toggle to 0, it only has the test set out. Right click, descriptive statistics, and voila, my mean squared error is 23.016. So what does that mean? Well, if I take the square root of it, equals square root of 016, you'll find it's about 4.8 years. So I'm guessing age plus or minus 4.8 years. Okay, that's what it's telling me. My forecast for age, my estimate for age, that's one standard deviation either way. It's standard error, actually, one standard error either way. And that, ladies and gentlemen, that's how you do principal components regression when you have to calculate those factor variables because you have to fill in the blanks. Some people would take shortcuts and use the whole data for calculating the means and standard deviations or for factor analysis, but you're not supposed to because you're leaking information that you would not have. We're supposed to consider the test set to be pristine and unseen data. So thank you for listening and have a great day.